I don't want to stand between everyone and happy hour, so let's get started. So welcome. I am Craig Freeman. I'm a UI technical architect based out of Denver, Colorado. And for the last 3 years, I've worked at Kenzan, which is a software consulting company, where I've worked on UIs and node servers in enterprise microservice applications. So today, we're going to be talking about the circuit breaker design pattern and what it can do for your APIs. So I want to start off quickly with just a rough scenario. So borrowing an example from the Hystrix library's documentation, let's say you have a 99.7% monthly uptime for your microservices applications in your e-commerce site. That means that your application will fail roughly 0.3% of the time. So 0.3% of, for example, 500,000 requests equals roughly 1,500 failures. And that translates to about 2.2 hours of downtime per month. So if we applied a value of $50 to each one of these failures, that'd be $75,000 loss per month, or roughly $568 per minute. These figures are making assumptions about frequency of sales and average number of users, abandonment rates, conversion rates, et cetera. But there's lots of variables involved, and the point is that there's potential for lost revenue and poor customer relations, which is a real business impact. So every minute counts. We need to do better. We need to fail faster. So here's the plan for today. For context, we'll quickly talk about microservices. That will lead us into the what, when, how of circuit breakers. We'll then look at some code examples and walk through a couple scenarios, and then we'll talk about how to move forward. James Lewis and Martin Fowler have been some of the main proponents of the microservices software architecture in the last few years. They define it here. It's basically a large application made up of a collection of smaller applications. They also lay out a number of characteristics of typical microservices patterns, but the one we're most concerned with today is going to be designing for failure. Microservices have many interdependent services, and it should be expected that any one of these dependencies can and will fail at some point. There are multiple ways of designing for failure, and therefore multiple reasons for doing so, but for the purposes of this talk, we're aiming to avoid degrading the user's experience and preventing loss of revenue. We can do that with these three here, graceful degradation, monitoring, and resiliency. So first up, graceful degradation. The idea is we want fast user feedback, and that theoretically and hopefully results in decreased abandonment rates, but we can achieve this using fallback methods, which minimize the amount of network traffic, giving upstream services time to recover, and giving us options for how to respond quickly. Next up is monitoring, which can be done by consuming streams of metrics and logs. Now, in theory, you should already be doing this in your applications, but just for review, here are the golden signals that we want to measure. Latency, traffic, errors, and saturation. Lastly, we can add resiliency. And at an infrastructure level, we want to detect the load on a system and be able to scale our services up or down. If we don't add resiliency properly, it could prevent auto-scaling, which we'll talk about in a bit. We also need to worry about fault isolation. We want to help shed server load and fail fast to prevent any single dependency from causing unnecessary stress, like event loop queuing. Repetitive failures in a short amount of time can overtax services and can lead to cascading failures, which can bring the whole system down. Obviously not great. So now that we've covered how to design for failure, what can we use to tie graceful degradation, monitoring, and resiliency together? And the answer is circuit breakers. From a general point of view, a circuit breaker is really just an automatic switch that protects circuits from overloading or short-circuiting. And in this case, in our case, the circuit is going to be the request and response cycle. In a software context, circuit breakers are a design pattern that we can apply to route handlers, or really anywhere we have another service as a dependency. A breaker will trip to prevent network requests for a predetermined amount of time after the error or timeout thresholds have been met. And it's important to note that we're not preventing failures, we're just failing faster. So let's dig in a bit how they work. There are a few breaker states to understand. So first is the closed state, where a resource either has not yet been tried, or it has been tried and it's not yet available. Next is the open state, where a resource was tried and was unavailable, and this is where the circuit breaker will trip. And then lastly, we have the half open state, where a wait threshold was met after the circuit breakers tripped, and the resource was tried again. So think of it like trying to pet a cat. First, they like to be pet, until suddenly their internal circuit breaker trips and the circuit's broken, at which point they proceed to murder your hand with teeth and leg kicks. You know you'll get hurt if you keep trying, so you have to wait a little bit before you try again, at which point the circuit is half open, but it's anyone's guess as to whether you'll keep your hand or not. So this breaker stayed open. A couple other key concepts. Important to note, we have the failure threshold, which is the circuit will break if the percentage of failing requests exceeds this percentage. We also have the timeout, where how long before the circuit trips if a request takes a long time. I'm basically reading the screen here. Wait threshold, also we have is how long before a circuit should stay broken before it does that half open request again. So we also have this concept of a rolling window, kind of behind the scenes. This is how the circuit breaker keeps track of successes and failures. So we have this window, this dashed box here. It's configurable time period. It's usually 10 to 15 seconds. And that shows the current bucket on the right underneath now, and then the previous X number of buckets, which are capped to the left there. Buckets are effectively, in other languages, they might be semaphores or thread pools. In the Node case, they're basically just a collection of requests for a given time period. We have bucket span, which is how long a bucket is open before it gets capped. And a new empty bucket is added to the window on the right. And the last bucket on the left is dropped into the dumpster fire. The last thing I want to go over is capacity, which is a number of concurrent requests allowed. So if the number of overall requests in a bucket span reach the bucket capacity, the breaker is going to trip. And additionally, if the number of failed requests in a window reach the error percentage threshold, the breaker will also trip. So hopefully you can see this. Let's walk through it. We've got the concepts behind us now. So I'll point out that this flowchart was heavily influenced by the documentation of Netflix Hystrix package, which is a Java implementation of circuit breakers. So blue is the invocation path, and red is the return path. So we'll start to execute the request, and we'll check if the circuit breaker was already open, whether the buckets are full, or whether the window's failure threshold has been met. If any of these have occurred, then we'll proceed directly to the fallback method. If none of these occurred, though, we'll proceed as normal and execute the function, or a request to an external service, in our case. From there, the library will determine if an error has, or a timeout has occurred. If they have, then we'll proceed to the fallback method also. But if they haven't, we proceed as normal, as if there was no circuit breaker pattern involved. The fallback method will either succeed or fail. It really depends on what you have it do. In a node context, this is where we'd pass the API value back to express to handle. So every time one of these decisions happens up top and on the side here, yeah, not square. The library is using data in the background. So based on the breaker settings, it's all behind the scenes, so it'll determine whether to break the circuit or not. So this is all done for you, depending on the library. So let's look at some code. Here we have a simple handler function, route handler function. It's pretty basic. There's really not much we have to do to add basic circuit breaker functionality. So basically, it's that. So we create the higher order function, the breaker function on line 13. We'll pass in the method that we want it to call, in this case, request.get. Then we change our code to execute this breaker. We'll pass in the parameters that we want the function to use. And all of this circuit breaker logic happens, again, behind the scenes. So this is a very small addition, a very small amount of code for a lot of benefits. Here's just quickly the diff. We're taking away one line, we're adding 3. We do have the option to edit the default settings. And these settings are available. I mean, it really depends on the library you're using. But in this case, I think I'm using Possum here, I'm able to change these 3 settings. So we have timeout, we have the error threshold percentage, which is the failure threshold that we talked about earlier. And then there's the reset timeout, which is the wait threshold. What I think is the biggest advantage to using this pattern is the ability to act on failures via the fallback method. In this example, this is where we provide a default value. But really, we can put anything here. We can pull from the cache. We can retry our original API call. We can do nothing. It's really anything we want. So besides the fallback method, we have a variety of events that we can listen to, and again, library dependent. In this case, we're reporting the request successes, failures, and timeouts, and the circuit breaker states to our metrics libraries. So I mentioned Hystrix earlier. It's a popular adaptation of this pattern for Java services by Netflix. But there are a number of JavaScript libraries available on NPM. In this case, 4 pages worth. So find the library that suits your project's needs and dig in. So now let's walk through a couple scenarios. First, I'll start with the success calls. So I created a demo microservices application. This is basically what it does. So a server that serves the UI and then also acts as a proxy to the API server. So in this application, I added some metrics for reporting. And I used the artillery performance testing CLI to hit 2 different endpoints on the UI server. One with circuit breakers, one without. So looking at the latency differences between the successful requests, both endpoints result in a 200 response. You can see the latencies are pretty similar. So even with circuit breakers applied, things work out to be about the same. In the next example, I created 2 endpoints that will always result in failures. So again, with and without circuit breakers. So the browser will make a request to the UI, and the API server responds with an error. We don't know why, it doesn't matter. Could be an application error, it doesn't matter. So Without the circuit breakers, each request will attempt to call the API server and result in a 500. But rather than every subsequent call making a request to a failing server, increasing the potential for cascading failures, the circuit breakers will try the request as normal. And if enough failures occur within that failure threshold, the breaker will trip, and the UI server will respond with a failure. So then every subsequent call during the wait threshold will immediately fail, and no request being made out to the API server. After a while, that half-open request is made, and either the breaker will close or it will remain open. In this case, it closed. So if you look at the differences in the latency metrics for the failed endpoint request, you can see the average latency for the endpoint without circuit breakers takes a longer time to complete than the request, whereas the endpoint with breakers has a very small, almost invisible, it's really hard to see on the right here, a very small average latency. So it's failing very quickly in comparison. Now we'll move to timeouts, and these are very similar to errors. Every request will sit and wait for the server to time out, unnecessarily stressing a service that obviously isn't working. The circuit breaker library will wait for that timeout setting's length before responding with a failure and tripping the breaker. So with a circuit breaker, you can translate a timeout into an error. So when you fail fast, the user isn't waiting forever. Any subsequent call during this wait threshold will immediately fail and respond with a 500 in this case. Again, with the half-open request will occur, and after the wait threshold, we'll get that half-open request, and the circuit breaker will either close or open, or stay open. So I think the metrics here are a little more interesting. On the left, we see no activity until the UI server times out after 2 minutes, and all of the requests are reported as 500s. It's off the charts. On the right, the endpoint with circuit breakers is failing really fast. You can barely see it on the right there. 500s come back almost immediately, and the latency is minuscule. You can barely see that. So the dark blue line here, really the only line, represents the rate of immediate failures of the endpoint with circuit breakers. You can barely see this light blue line on the right. So very few errors are coming back from the upstream endpoint when not using circuit breakers. They're almost 4 minutes apart. So without circuit breakers, we just potentially lost about $2,200 using the example from earlier. So lastly, we'll see what a difference a circuit breaker fallback can make. The scenario on the left is the same. Each request will slowly time out, but on the right, we can still do something productive. So in this case, we're responding with degraded functionality. So instead of responding with a 500, we can use the fallback to respond with a default value so the request can succeed. And for the metrics, again, the left is basically the same. We see nothing until the upstream server times out, and our UI server eventually sends back 500 responses. But the right shows successful calls coming back much sooner with a lower latency from failing fast. It's sort of backwards. So if you look at the rates of failure and success, the left shows the endpoint without circuit breakers failing once the sockets time out a few minutes after the endpoint with circuit breakers responds with a fallback, which is shown on the right. And I will point out that I'm using Datadog for displaying my custom metrics, but a lot of the libraries available will provide a server-side event, a stream event, of metrics that the Hystrix dashboard can consume. And this gives you really good insight to the circuit breaker internals, whether it's the breakers open or closed and how many requests and how many failures and things like that. Unfortunately, the project has been deprecated by Netflix for security reasons, so I'm not going to talk about that. So there are some cons to using this pattern. A little more code means a little more overhead. So the performance difference should be negligible, but depending on what your fallbacks and handlers do, it might be a little more. Might be noticeable, but so if you request a resource and it fails, the circuit breakers will prevent subsequent calls to the service. And if your upstream container has auto-scaling set up to respond to an increase in requests, you may end up preventing your container from scaling properly. This is where some fine-tuning is needed. So first, basically expand the size of your auto-scaling group, and only when the max of the scaling group is reached should the circuit breaker kick in. And this is something you'll have to try out. You'll have to tweak the settings on the circuit breaker, failure threshold, timeout, bucket size, and things like that. So now that we understand the pattern, there are a couple things we can do to take it to the next level. If you're using TypeScript or Babel, you can transpile your code, and you can leverage the decorator pattern, which will make it very, very easy to add the circuit breakers to your route handlers. You can also try the retry pattern, or the exponential backoff algorithm, there we go, in the fallback method. You can also respond with cached data or provide a default response from the fallback. It doesn't have to fail. Another thing you can do is you can add a service mesh, which is basically a configurable infrastructure layer for communicating between the services in a microservices app, and this provides a global fallback method. Additionally, you can use a runbook. These are great for new developers coming on to your project, or just recording ways of debugging that you may not come across on a regular basis. So I recommend those. And then there's the fine tuning. You can do this with performance testing. You just want to make sure that the settings that you're using aren't preventing that automatic load balancing. And also chaos testing, which are essentially fire drills. You can leverage the runbooks and basically refine your responses to incidents that you have. So that's it. Hopefully you leave here understanding the relationship of circuit breakers to typical microservices ecosystem, as well as why we design for failure through graceful degradation, through monitoring, and by adding resiliency. I hope that you take what we've learned for the circuit breaker pattern and apply it to your microservices, and so that your applications can fail faster. Are there any questions? We got some time, so available to answer some questions if there are any. I think I heard you. The question was, if you're building a traditional app, would you have the circuit breaker on both requests? Front end or back end? So it's traditionally back end, but it's really just service to service. So if that happens to be front end to back end, then you're able to do that. Some libraries allow you to incorporate this code in like Webpack. In this case, I don't think it's necessary because the UI and the UI server that's making the request to a different service are on the same service. So if one's down, they're probably both down. But yes, it is possible. Great. Well, I'm Craig Freeman from Kenzan in Denver. We do have a booth up in the West Ballroom D if you want to come talk microservices or serverless or PWAs, or if you just want to come say hi. My slides will be available on craigfreeman.net later today, and thanks for attending. I hope you guys enjoy the rest of the conference, and let's get some beer.